Welcome back. So this is section 3.8, Newton's method. Okay. All right. So Newton's method, this is a method, very useful method for finding approximate solutions. Okay. It's one of the most important methods. Let's see what it is. Here is an example. Suppose that a car dealer offers to sell you a car for $18,000 or for payments of $375 per month for 5 years. You would like to know what monthly interest rate the dealer is in effect charging you. Okay, this is a tedious problem, but essentially to find the answer you end up having to solve for this equation. Notice this is a 60-degree polynomial. It's not easy to find a solution. Well, but to find a solution of this, we can do something like an approximate solution by plotting this function. Okay. When you plot that function, you know that when x is 0, you have a solution, and then somewhere here you have a solution. And that number is between 0.007 and 0.008. You can zoom in and it will come to approximately 0.0076. Okay. For more accuracy, you would zoom in some more. All right. All this is based on just this particular expression. Okay. Graphing that expression. Now, this is one way of finding an approximate solution. A faster alternative is to use a calculator or computer algebra system to solve the equation, okay, numerically. Well, in other words, you want to find the root up to 9 decimals, so on and so forth. So, where do these calculator and computer algebra systems come up with their methods? Okay, so how do these devices solve equations? They use a variety of methods, but most of them make some use of Newton's method, also called the Newton-Raphson method. Okay, Newton's method is also called Newton-Raphson method. We will see how this method works. So basically the method is very useful because it is programmable. So you can program a computer algebra system or a calculator, and that's the advantage of an approach like this. Okay, you can solve tedious equations like this using this method. Okay, what's the geometry behind Newton's method? Okay, so you have your curve here, right, in blue. You want to identify R. R is where you get a solution equals 0. That's what it means to be x-intercept. Y is 0. So you want to identify R. Well, you don't know that R. It might be 0.0007, whatever. Well, you can start with an approximation. Let's call it x1. Maybe your approximation is 5. Yeah? So your first approximation is called x1. For x1, you see what point you get on the curve. So that is x1, f of x1. Draw a tangent to that curve at that point. That tangent will hit the x-axis somewhere. Let's call that x2. Aha! Now you got a better approximation. You're getting closer to it. You do the same thing. Draw a tangent, find its point. Draw a tangent. Aha, you'll get closer. That's your third approximation, and so on. That's the point of the Newton's method. You're using the tangent line to get closer and closer to your actual root. So we start with the first approximation x1, which is obtained by guessing. You almost always guess, or from a rough sketch of the graph, or from a computer generated graph of f. Consider the tangent line. Look at the x-intercept. Call that x2. The idea behind Newton's method is that the tangent line is close to the curve, so its x-intercept is close to the x-intercept of the curve. Because the tangent is a line, we can find its x-intercept. Okay? Likewise, to find a formula for x2 in terms of, now, how do you find x2? Oops. How do you find x2? You understand? Well, you have a tangent line and the x-intercept of the line is x2. Well, what is the x-intercept of a line? You need equation of the tangent line. Do we know how to find equation of a tangent line? Yes, we do. How do we know that? Because we know the derivative that gives you the slope and you have a point. Point slope method gives you equation of the tangent line. Once you have equation of the tangent line, the x-intercept gives you the second point. Okay? So that's what it is. This is equation of the tangent line. This is the derivative. Okay? And the point is x1 fx1. So y minus y coordinate equals slope times x minus x coordinate. That's your equation of the tangent line. Well, move the fx1 to the other side, right? Or not. Okay. How do you find x-intercept? You set y0. Okay. Setting y0 gives you the x-intercept. X-intercept is x2. So I'm plugging x2 for x. Solve for x2. Well, that's fx1. This I'll divide by this quantity and there is a negative and then eventually add x1. Okay, if you want, write this on paper and solve for x2. Divide by fx1, f prime x1, both sides, gets rid of this. You have fx1 over f prime x1, add x1 and whatever is left is x2. Now x2 is a better approximation. It is called the second approximation. You repeat the procedure with x2 as your approximation using tangent line at x2 fx2. Okay, so with x1 you got a tangent line whose x-intercept is x2. With x2 you get another tangent line whose x-intercept is x3. Notice you are getting closer and closer to R. Okay, so in general the formula is given by this. If xn is your nth approximation, xn minus fxn over f prime xn, that is your next approximation. Okay? So if n were 1, giving x1 here gives you x2. If n were 2, placing x2 here gives you x3. I hope you understand. Starting with x1, you can get x2 using this formula. Starting with x2, you can find x3 and so on. Now this is a big if the numbers xn become closer and closer to R, as n becomes large, then we say that the sequence converges to R and write limit n approaching infinity of xn is R. So if the xn's get closer and closer, then their limit is R. Okay? Hopefully. This is what you're hoping for, but this doesn't always happen. That you have to be careful. Newton's method doesn't always work. Well, one place it will not work is when the derivative goes to 0 at any of your approximation. If the derivative is 0, you have it in the denominator. You cannot use this approach anymore. All right. So keep that in mind. This is the important formula. Xn plus 1 equals Xn minus Fxn over F prime Xn. Okay. So the next one is an example. Okay. So I'll come to it in a short while.